Hello, my name is Kevin Nguyen, and this is my lab for oscillation. So, introduction. Our goal is to examine the motion of the spring oscillating in an arc, and we're going to use a tracker to track the motion. Then I'm going to create a computer model for the spring oscillating. Then I'm going to compare both the model and the experiment position in both the X and Y axis. And then we're going to look at the graph for the change in energy versus time of the model, and then we're going to look at the changes in kinetic potential energy of gravity and the spring potential energy. So the formulas I used were the period of oscillation, which is 2 pi times square root of m over k, and then we're going to isolate k by itself, which is this formula. K equals 4 pi squared times m over t, and we're going to use this equation to figure out our spring constant with the oscillation. Then we're going to use energy principle, which is the total energy is equal to all the energy component, which is going to equal to 0. Then I use Newton's second law for velocity and position, and then the equations for kinetic and potential energy. We also use Hooke's law, and then figuring out the F net by adding all the forces together. So first, setting up my tracker, I set up my coordinate system at the fixed attachment point, and we know the length is going to be of the spring is 0.7 meters. Our mass of the metal ball is 0.42 kilograms, and our frame rate is 10.5 seconds. So after tracking my metal ball oscillating in the arc, this was what I got for the x-axis versus time. Then our period is going to be, I looked at the fourth oscillating, so the fourth period, which was 6.458, and then I divided that by 4, which is 1.6145 seconds, so that's going to be our average period. Then now with this info, we could find out our spring constant by this equation, which is going to equal to 6.088 newtons per meters. And then since we know, now we're going to look for our relaxed length, and we know that it's going to be static equilibrium, so Fg equals Fs, and then we just isolated for L0, which is our relaxed length, and we saw for K already, we have L, we have Mg, and so we just plug it in, and I end up with 0.0528 meters. And for our system, we're going to be using the mass, the spring, and the earth, so everything. And because we're doing this as our system, we have no energy transfer to or from the surroundings, so we're going to equal this to 0. So this is our code. So I changed the mass to 0.42. Our position, the starting position is over here. When I start on the tracker, our initial velocity will be the change in distance between the two divided by time, the first two measurements. And then we're going to use a small delta dt because so we have to have a smaller time than the 10.5 seconds. Then we're going to get gravity, the spring constant, which we saw, the relaxed length that we also saw. And L is going to be our change in length, which is going to be the position of the ball minus the position of the spring. Then L hat will be L over magnitude of L, and S will be the magnitude of L minus the relaxed length. And then this is going to be setting up our initial energy, so kinetic energy, potential energy, spring potential energy, and total energy. So we use the equation right there, and then we add them all up for our total energy. This is what we did there. And then F gravity is going to be the mass of the ball times gravity. The spring will be the Hooke's law, and then our F net will be the addition of both of them together. Then we're going to use Newton's second law for our new velocity and position, which we'll be using to update the length of the spring. And then this is going to calculate the energy changes. So we're going to use the energy principle. So we're going to do the same equation for K, potential energy, and for both the spring and gravity. But then delta K will be the K minus the initial. Delta UG will be UG minus the initial UG. And the same for the spring. And then we're going to add up all the deltas for the delta E. And then this is our computer model results. So as you can tell that looking at energy, you see that's at 0 constantly. So this shows that the energy principle is satisfied because the total energy is constant at zero because nothing is added to, like no additional work is added to our system. And from this picture, the only thing touching the system is the attachment of the spring right there, but this has no displacement because it doesn't move at all, so there's no work done. And as you can tell, so you can see like as the spring goes up, the change in the spring potential energy, there'll be a change in the gravity, and there's also a change in delta K, but they all equal. You add them all together, and it's going to equal to 0. And our comparison. So this is the X and Y for both the model and the experiment. And you see the period for both of them are very close. It's 1.67 for the X position and 1.7 for the Y. And the amplitude is what mainly differs from the experimental and the computer model. And this is because of probably the drag force, air resistance, slowing it down. And an additional reason why they are different is it could be because of human or technical errors such as round-off error. And they also don't have to be like the same because both axes is affected differently since it's oscillating in an arc. So the y-axis could be affected by both the spring force and the force of gravity, and x-axis is only affected by the spring force. And that's it. Thank you.